All right, so I just wanted to finish up this material on pressure from class today. So we already talked about this. So we're looking at the idea of a two-dimensional distributed load. Here we see it. It's a function of both x and y. We could think of it as exerting some sort of force on this plate that is below it. Because it's a function of x and y, the units of this, we figured out, would be newtons per square meter, which really gives it the units of pressure. Finding the total force would be found by taking that distributed load function and integrating it times dA, which then we realized actually looks like the volume that's underneath the little square of dA. And so finding the force or the total force of a two-dimensional distributed load could be reduced to thinking about finding the volume under that curve. So if you go back to the one-dimensional distributed load, you can see how that makes sense, because if you remember when we had a one-dimensional distributed load, like something like here's my beam and here's my W of X, the force was just ended up becoming the area under the curve. So we have one more dimension. It makes sense that we go from area under the curve to volume under the curve. So that kind of leads into a really common application of this idea, which is water pressure or any other fluid pressure. So in class, I showed you that the pressure under a depth of water could be found by taking the density of the fluid times the acceleration of gravity times the depth. Z is the depth that we are under the water. Sometimes we shorten this, so the pressure, instead of just saying rho g z, we write it as gamma z, where gamma is just rho times g. So we're just combining those two. So where we're going to put the total force due to a pressure or a two-dimensional distributed load is going to be called the center of pressure. And so we're going to kind of look at that, but we're going to look at it for the specific example of fluid pressure, because we know how that behaves. So here is a situation where we have a plate underwater, and we're thinking about how the pressure due to the fluid behaves. The idea, if you can sort of see here, is we're starting the plate at this depth, Z1, and the plate kind of goes down to a depth of Z2. So the pressure or the height of the distributed load at the beginning of the plate could just be written as gamma times Z1, and the pressure at the bottom of the plate could be written as gamma times Z2. This plate has a uniform width. They're trying to show you here. The whole width, of course, is going to be B, but they've placed the force due to this water pressure at the location that we're calling the center of pressure. The B over 2 and the B over 2 here are just shown because it's going to be along this line. It would be in the middle of that plate, but it's going to be skewed towards the deeper depth. But there's something that we can do with this. If you look at it, you can see that in general, a side view is like a trapezoid, but is also three-dimensional, so it looks kind of complicated. But if we have a uniform width that we're looking at, that B, if that's the same the whole way along, like from depth of Z1 to Z2, if the width of the plate is the same, we can do a simplification. If we go back to this, we're sort of looking at it from this viewpoint. So we're looking at it from the side, okay? So that, again, we can actually change the flat plate and actually make this into a two-dimensional problem. So what we've done is we've taken the pressure, which was P1, which was gamma Z1, but we're going to multiply it by the width of the plate. And so that we could then say, by looking at the plate from the side view, where the B, the width of the plate, goes into the page, so the idea, again, if we go back to the previous slide just really quickly, go back here, that the B is the dimension that's like into the screen here. But what we've done is, because it's uniform in that direction, we've just changed this from a two-dimensional loading to a one-dimensional loading. But to get our distributed load W, we multiplied the two-dimensional distributed load, which had a value of P1 at the top, and we multiplied it by the width of the plate, B. And so now, when we're looking at it, we've changed it into a 2D problem where we're just finding the total force is the area of the trapezoid, and the location P is at the centroid of the trapezoid. And so we can simplify it a lot, and that's really helpful. So you're going to see problems, and they'll talk about, like, if you're looking at maybe a gate underwater or a dam, but then they'll say that it has a width of, 4 meters or something. The way that we can change that from a three-dimensional problem to a two-dimensional problem is just multiply our pressures at the top and the bottom by the depth or the width, which is the dimension that's going into the page, and sort of compress it into a 2D problem with a one-dimensional loading. I hope that makes sense. So we aren't always blessed with a flat surface that the water pressure is exerting on. You might have something that's curved, which, it could be doable. It would involve some fancy integration in order to find the pressure. Keep in mind that the pressure is always going to be perpendicular to the surface, because that's how pressure acts. But there's a way that we can actually simplify this problem. So we're going to take a look at this, because this is a technique that we would use a fair amount. So here is sort of the side view of that curved plate. Notice again that they've multiplied the pressure due to the depth by the width of the plate, which is B. And so this is actually going to make it into a 2D problem. And so we could do this if we knew the function of this curve. We could find the area under the curve. We could find its centroid, etc. But we can do something actually a little bit simpler. We can sort of separate it into components that are easier to find. So for instance, what we've done is we've tried to break into two dimensions. And one of them will look at vertical forces, and the other one will look at horizontal forces. And And the idea being is that our total force is the vector sum of these component forces. It's like breaking forces into x and y components, and then you can find the magnitude and the direction once you have those x and y components. Now, in this particular problem, our plate starts underwater, so there are two vertical forces that we have to think about. There's this top one is just due to the pressure due to the water above where the plate starts. And so that actually is uniform because everywhere along here, the depth is the same. So the height of this is, the P1 would be equal to gamma Z1, which gamma is rho times G. And then B, that's because of the width of the plate. That's the dimension of the plate going into the screen that isn't shown here. And so this is a constant loading function because we're at a constant depth the whole way along. And so we could just simply find, the force down due to the depth of the water where we are at the top of the plate. Then we have this right here. This is the weight of the water that is sort of hemmed in by the plate, the horizontal line, and the vertical line. So it's really outlined. Let me see if I can just outline it for you. The weight of the water that we're looking at, I'm going to outline by the red pencil. And so we would have to figure out what the volume of water is there, multiply it by the density of the water, and then also multiply it by gravity. So we have two forces down. One of the forces is due to the water pressure at the depth equal to the top of the plate. Then we have in this red region some water that has weight. It's going to act straight down. We'd have to find the volume of water to find that total weight. And then finally, the horizontal force, this is where we have we're dealing with the fact that the pressure increases with the depth. So at the top of the water right here, notice that the strength or the height of the distributed load right here is actually the same as it was right here because you're at the same depth. And then as we go down to the very bottom of the plate, we're at depth. This is equal to gamma Z2 because we're at a depth of Z2, and the pressure at that location would be Z2. And then, of course, we are multiplying it by the width of the plate, which is the dimension that goes into the screen. So we would need to find, so the force AD would be the area of the trapezoid that we have created with that distributed load. So let me outline that with green. I'll just kind of say it's like this. So the trapezoid looks like this. And so that is our horizontal force. So now we've broken our forces into two components. The horizontal component was that FAD, and we had in the vertical direction, we had the FAB and the weight. And so we would simply add those together. We could do the Pythagorean theorem to just find the magnitude of the total force. We could also find the angle that they're at by simply treating those as x and y components and finding their angle with the horizontal, like we would with any other set of vectors that we've broken down into x and y components. And so this is a technique that I think you're going to want to use maybe on some of the problems. It makes it a lot easier. So here's just a little bit more like talking about what I walked you through in terms of what all those different forces are. And I'll just let you look at that for a little bit. Of course, you can also see on this picture, they've chosen the locations where each of these forces act. You know, the location for FAB would be right in the middle of the rectangle. That one's fairly easy. This location would be at the centroid of this shape, which is, you know, this amount of water. So that would take some integration. And then the centroid of FAD, we could consult our tables to see where we can find the centroid of a trapezoid if we wanted to do that. And so this would not only allow us to find total forces, but in this picture we're talking about where we place them, where their centroids are, and then we could sort of treat those if we're trying to find the overall centroid. We could do a moment analysis of that. And this is where we would talk about that. We could just, you know, we could use point D as our pivot point, and we could talk about the moments due to each one of these forces, add them all up. That would be equal to the resultant force times the moment arm, and we could find that. All right, so that finishes up this material.